heard of situational awareness. I don't know if if anyone's going to claim operational awareness, but if not, I'm going to coin the term. And I'm really just applying the fact that we need better situational awareness in the operations space, which is where I came up with the OA terminology. And I personally think this is the biggest challenge that we have facing ICS, is a lack of operational awareness. What I mean by that is just a holistic understanding of what's going on our networks. We have a tendency now to be forced to use technology that we don't really have a say in. You know, our cars are more sophisticated than they've ever been. If you have a fault, we don't really know. We can't troubleshoot it. It's not like the good old days used to be able to lift up the hood and take a look and roll up your sleeves and get at it. You just can't do that anymore. So we're increasingly forced to use technology more, and as we do, we have less understanding of what it is we're doing. So with that, I also wanted to highlight here that there's been a number of discussions leading up to and including S4 today regarding deep packet inspection, so much so that even Bernie Sanders was forced to bring a giant cardboard cutout of one of Dale Peterson's tweets specifically talking about DPI. So it's obviously a very hot topic, and we're going to continue that theme and give you a little bit of a sense of what DPI is from our perspective. So a little bit about me. My name is Matt Cowell. I'm with a company called Ultra 3 ETI. You could probably tell from my accent, I'm based out of the Chicago area from the Midwest via the UK. I've been doing automation in some capacity for at least 15 years, starting as an embedded engineer, working my way up through manufacturing, also in sales and support, systems integration. So I've got a fairly good holistic view of things, and it's been interesting to see where we've been with cybersecurity regarding this space, and I'm excited by the hope that we have here at S4 this year. Ultra 3 ETI, quick introduction to us. So 3 ETI, you may not have heard of us. It's a very cryptic name. It's kind of a memorable or forgettable name, depending on how you want to look at it. But heavily, we got a lot of history in the DoD and government space. So if you're in the OT ICS space, you never heard of Ultra 3 ETI, that's probably why. But I am here solely for this purpose. So I have no DoD or federal experience, although that is the core of our business. But really, the key takeaway there is that we've been entrusted to work with very high risk, very high criticality networks, and that applies to obviously the space in which we're talking at and presenting today. So we're going to talk a little bit about OT anomaly detection. Again, there's another buzzword, a lot of hype around that. And we're going to then factor in how DPI technology, deep packet inspection technology, applies into the OT space, looking at some examples of that, some application instances, and then we're going to just do a little bit of a commercial for the Cyberfence product, which is ultimately what this is here under the sponsor stage pretense. So, is anyone doing the S4 CTF in here? I imagine if you were, you'd be up there now. Oh, we've got one little hand. There might be some CTF clues towards the end of the presentation, so there's a little incentive to stay, even if I'm kind of dragging on a little bit. All right, so I personally believe that today's biggest OT challenge, as I said before, is ultimately a lack of understanding. And the phrase here that I have, the lack of monitoring and understanding of normal conditions to be able to discern abnormal. We do not know what normal looks like, therefore we cannot know what abnormal looks like. Are we looking? If we are looking, are we looking enough? So I've broken this down into OT and anomalies into 3 classifications. The first one is system anomalies. And what I mean by that is really the things that an operator can detect. The overall system is running right because a certain amount of widgets are coming out at the rate you would expect them to. Or the blend looks right. Or in the case of DuPont, you know, the color of white looks white, as we had earlier. You may get some deviations, maybe like something doesn't sound right, and an operator's like, normally this doesn't make that sound or this smell. And those are some things that you can detect that potentially there's a system-wide anomaly. Ultimately, though, system anomalies I classify as human detectable anomalies. You know, a good example of that could be, you know, the plumbing in your home. Something goes bad, you smell it. If you had the ability to see in the pipe, you could have maybe done some sort of preventative maintenance, but unless you're looking, you don't know, and it's usually catastrophic once something happens. The other classification here I have are network anomalies. So has our network changed? Have we got a new topology? Have we got a new device? Are new devices talking to each other that they weren't before? And if they are, what type of communications exist between those devices? So data flow, data type, and also data frequency. How often are they talking? Are we seeing a denial of service type approach here? And then the third classification, I have a device anomalies. So something at the very end is not working right. Maybe it's a fault, maybe the configuration has been changed, maybe the firmware has been updated and now we're getting unexpected behavior, or maybe there was a new application installed in the case of a host-based system. So those are the three types of anomaly that I tend to define. And we've got network anomalies and asset device anomalies. And to me, these are the ones that you can detect. These are the ones you can be active in understanding. And from those baselines, you can then start to detect abnormal from normal. And the other thing I was going to say is that with regard to anomalies, in my experience, when we look at control systems networks, especially in a troubleshooting capacity, one of the first things you ask for is a network map. Can I get a network map or a network block diagram or something? How many of you find that that's easy to get? And for the record, I see no hands, but I also am kind of blinded here. So I would agree with that. The amount of times I've asked for what I consider relatively trivial data to help me in my job to troubleshoot is seldom available. So if we don't even have that level of understanding of our networks, we definitely have a long order to be able to detect these sophisticated anomalies. All right. So having a deep understanding of your control systems is key to detecting anomalies, and you can see where we're starting to go now. So moving on, I think we all know this. I'm sure this is preaching to the choir, but it's worth going through some of these just to make sure that we're all in agreement. So these are some of the key attributes that I find significant or poignant regarding OT systems. So messages tend to be sent in clear text, and bonus points for anyone who can tell me what that message little snippet is there in the top right-hand corner. It's a Modbus 1.6, so I think that's a right multiple, I'm not sure. Anyway, messages are sent in clear text. Also, there's typically no authentication, so there's no validation that you are who you say you are, and therefore I can trust you. Typically, there's no integrity checking. So if I send the message, I just trust that once it's gone on the wire, it's good. I'm assuming that it's got there, and I'm assuming that it's got there in the same way in which I sent it. You also tend to get more complex protocol design. So anyone dealt with DNP3 here? Okay, if you do, then you'll start to appreciate some of the complexities of how complex protocols can be. Don't gauge industrial controls protocols by Modbus TCP. Also, we tend to see lightweight NICs. So you have an embedded device, and you've put some sort of NIC in it, and it has some relatively light resource capabilities in terms of what it can do. We've also seen a trend for poorly implemented protocol stacks. And also, it's not uncommon for us to get the standard protocols we expect, as well as some we don't expect, some proprietary protocols. So my device talks Modbus, but it's also doing a couple of other vendor things that allow me to do uploads and downloads and so on. Also, you tend to get numerous insecure interfaces, and when I refer to insecure interfaces, I'm speaking specifically about HTTP, SNMP, Telnet. We've heard about that today, especially if you were in Chris' systrunk session. Obviously, increased interconnectivity, and as a result of that, a lot of business needs driving that interconnectivity without really understanding the risks. And I think the best example of that is the Mirai botnet, or any botnet that we've heard about today, where a series of embedded devices have been thrown out there. They've got the technology in to do it, but they aren't secure, and there's a certain risk associated with that. And also poor bounds checks. ICS CERT had a statistic on that. I believe 30% of the vulnerabilities that they reported were a result of poor bounds checking in coding. It's also too important to note that IT systems are very unpredictable. There's a lot of user variation there, which requires a lot more sophisticated anomaly detection. OT is less so, right? OT is fairly stable, fairly repeatable, fairly predictable. And obviously, we are challenged with very long life cycles. These things you can't just go and flip a switch, change something out, and and set it up again. So would we all tend to agree with those attributes? Anything there that anyone disagrees with? Okay. So that sets the playing field for where we're going with this. So As a result of those behaviors, we have this insecure by design technology, and as a result of that, there are inherent vulnerabilities that we have to contend with, specifically sniffing and eavesdropping. We've got messages in clear text. That means we are also vulnerable to man-in-the-middle attacks. We also are vulnerable to unauthorized changes or commands, as well as spoofing, corruption, denial of service. These are all things that we have to contend with as attack vectors, but ultimately it ends up with the device being owned. Here's a practical example, very, very unsophisticated demonstration here with some very crude animation, but we've got a PLC that is talking to a VFD, which runs a motor as part of a very critical process, and there's an HMI as the window into the system. So this motor has the capacity in this scenario to go 0 to 100,000 RPM. But the process requires you to only ever go as high as 63,000 RPM. So the HMI, we code the HMI, and we set limits to that. So the operator can only set a value between 0 and 63,000. Additionally, if we want to put another error, bounds check, we can put it in the PLC. And that also says you can only go between 0 and 63,000. However, the message from the, do I have a laser here? The message from here to here, because there's no integrity checking, once, if somebody else comes in here, and they're unauthenticated, and they send a different command, they are not held to those same bounds checks that you have in the PLC or the HMI. So now we've just told our VFD to go, what did I say, 85,000 RPM, which puts us into the danger zone, and boom, we've ended up with some physical manifestation of our process. Bonus points for anyone who gets the references to 85,000 RPM and 63,000 RPM specifically. Really? Stuxnet reference? All right, all right. Okay, and because this is a network level discussion, it wouldn't be complete without some reference to the OSI 7-layer model. So we have our OSI 7-layer model. I'm not going to go into specific detail to that or into the TCP IP model, but the reason I'm going to highlight this is this identifies the layers of the protocol stack which the devices specifically are looking at. So in the case of standard firewalls, stateful firewalls tend to look at the IP layer and they look at the TCP layer. Agreed? And then perhaps the MAC layer as well. Where we're going with this, though, is deep packet inspection or application-aware firewalls need to look at the whole thing. They need to be able to digest not just the headers, right the way down into the data payload and make some decisions based upon that. So where I'm going with this is the application layer content is the most important content in that message. That is the stuff that defines your process. So this is the most this is the content that could have most adverse impact to your control system. So, what do these represent in the real world? We hear commands, we hear application, Modbus TCP, payloads, for example, but what this actually relates to in the real world is really what ties this all together. This is the part that should be the most alarming. This ultimately defines the set points. Your set points for your process could be temperature, flow, pressure. I've given some examples there. It could also be the process variable, the actual value that I'm reading from my process back. It could also be the alarm limits that define our safe zone, and if we go outside of that, we end up in an unsafe situation. They also represent the digital inputs and outputs coming from various sensors or going to various actuators. Also analog inputs and outputs, and also the device mode. So these are all very important parameters when you break them down into what they mean in your process. So as I say there, this represents way too much risk for us not to take this seriously and take an effort to secure. Here are some examples of taking that and applying it to actual data sheets. So in this case here, this is a tamper-proofing variable that you can access. And remember, this is in clear text with no authentication. So if I want to turn off my tamper, I can do so. Same thing here with VFD speed references, with alarm masking, so I can mask alarms. Again, unauthenticated, unencrypted. Values here on my VFD again. I can control access control. So in the case of BACnet, you may have your door access control system tied to that. So I can open my door through that. I've got speed reference again there. So these are actual, and this one I put up, I thought this was interesting, go to emergency mode. I don't know what that means, but if I can block go to emergency mode when it's emergency, I'm guessing it's probably going to have some pretty bad outcome. All right. So now we've set the table as to where we're going with this. We've talked about OT, anomalies. We've talked about the value of starting to parse that content, what that can mean in the real world. And here's where DPI technologies start to be explained. So what do we get with deep packet inspection technology? So first thing is you get way more enhanced visibility of the interactions between your devices. So you're now not just looking at the header information, you are looking at the command that's being sent, the value that you are telling something to be. So I'm setting a set point and I'm setting it to this value. You get much greater visibility of that, operational visibility. You also now, because you have access to that and the visibility of that, you can start to enforce those rules down to the command and value level. And you can start to enforce a policy that's more consistent with your process. So you know what your process should and shouldn't do. You know the tolerances. You can now start to lock those down at the network layer. You also have the option to lock down now specific functions that you don't use. So when I have a Modbus capable device, I keep going back to Modbus, but I want to be able to read from it, I want to lock everything else down. And a great example of that is up in the CTF, which I'll talk a little bit about later on, where we're using Cyberfence to do that. We've set certain rules that you can get access, and certain commands are locked down. You don't necessarily need all of your commands open just because they're there. And the endpoint doesn't usually give you that option to shut that down. We now also have the ability to detect configuration changes or firmware changes that may take place at that endpoint. That is stuff that's usually exercised over the network. I want to do a firmware update, I do it over the network. I want to make a configuration change, I do it over the network. So now I have the ability to lock that down as well. I also, this is a shocker to a lot of IT guys, but the validation of messages. You can send a malformed packet to certain devices, and I won't name anyone specifically, where it will cause an out-of-bounds scenario, and that device will just lock up just because you sent it the wrong packet. I think one of the guys that presented earlier was referencing, I think it was Sean McBride was referencing the URL Frosty that the CyberX guys folks. Just taking a specific HTTP command and sending it, and that just bricks the device or causes some outcome. So actually validating that message per the protocol standards sounds very trivial, but is actually very important. We now also set limitation of the messages and commands to prevent unsafe scenarios. So we are stopping the potential insider or the inadvertent operator making a mistake because they are bound to that, they are unable to do that, which obviously limits the impact of potential human error. And other key things with DPI, they've got to be passive. It's got to be a passive implementation that has no interruption to existing systems. Obviously, change management is a big thing in OT. We don't want to have to go through this whole laborious exercise to do something and break something. So we've got to have a passive implementation and reduce the risk of interrupting something that's already running. And ultimately, what this gives you is a holistic baseline of your application. So you now understand everything. Who's talking to what are they saying, what's being said, how often is it being said? Okay, so DPI essentially validates and enforces the control operation as it was designed. Here's a common OT architecture, referencing the Purdue model here. So I think we'd all agree that we've got level 0 here with our sensors and actuators, which are then wired into some sort of appliance. I've got a VFD here and some PLCs. And these are usually network capable, and they talk up to our host stations where we run the software to manage these and supervise these, and take it even further where we can start to manage that at a much larger scale. What I'm going to focus on here is this point. This point to me is the most important piece of the pie here. This is where our electronic communications networks become physical. So if we can control this and have better understanding and awareness at this level, we've got a much greater chance of managing these here. Now, you could argue if you've got physical access to this, you could jam a wrench in the gears, or you could cut the wires on the motor, or do something, or short out the switch. If you've got physical access, all bets are off. But this is the point from a network standpoint that you want to have the most enforcement of your control in my philosophy. So I'm talking here about deep packet inspection. I've talked about Modbus a couple of times. I'm going to now start to apply what that deep awareness gives you in the context of different protocols. So in the case of Modbus, you've heard me say about function codes and register numbers and data and node addresses. These are all parameters in a standard Modbus data exchange. And then Ethernet IP, same kind of thing but different language. They now refer to more of an object instant class model with attribute IDs and then data. DNP3, again, the language changes a little bit, but you've got addresses, objects, you've got different messaging, different function codes. Then same again with BACnet. So the common theme here is that you start to see that there are commands and values which are essentially defined in different ways, but they are the core of what our process is doing here. Now, the other thing I'm going to throw out there is, how many of you think there's a skills gap in our industry? Yeah, I see a few hands. I would agree with that. So we already have this skills gap, and now there's this English guy via Chicago standing on a stage saying, well, we need to look deeper. We need to be able to understand and manage this. So the key part of this is that we do have a skills gap. We recognize that the managing and enforcement of this has to be done in somewhat of an easy manner. I think we'd all agree with that. And many of us use DPI. Wireshark, I think, is the best free tool that I use on a, well, not daily basis, but a common basis. And essentially, we're already doing that with our dissectors. So if you break open a message here, we've got a Modbus read function register. You look at it from a layer 2 perspective. You look at it from a layer 3 perspective. These are all things that we can do with standard firewalls. And then we start to break it down, layer 4 again for ports. And now we start getting to the application-specific content. And I love these dissectors because it now tells me that I've got a read register at this address 8000 with a word count of 1. Otherwise, I've got to start looking in here and deciphering that like I showed on the previous slide. So we're already using it, and we already value that to some capacity. And DPI, as I said before, it's the new buzzword. Even Bernie's getting on the case. And in addition to that, we're getting a lot of other pretty exciting acronyms. Next generation firewalls, next generation antivirus, next generation blank, or something as a service. You know, we're talking now like even SOCs as a service or NOCs as a service. I don't know if that's even an acronym yet, but there are a lot of as a service type things you can subscribe to. The key thing I want to point out here is that just because somebody says they have deep packet inspection, it's on you to understand what that means, because not all deep packet inspection is equal, and it's one of those terms that's going to be thrown out there a lot now. Okay, so here's what 3ETI's position is regarding DPI for OT. This is how we define it. The solution obviously should be designed for the OT environment, and as I showed you before in the Purdue model, where we think the most hardening is required is done at that level 1. That's where it should be designed for. It should be designed to reside there. It should have a DIN rail mount. It should be powered accordingly, 24 volts DC is typical. It should have the noise and environmental specs, for example. It also needs to have full OT protocol awareness, and what I mean by that is not just looking for signatures. Don't just try to do pattern matching on a signature. It needs to understand the protocol. And as these protocols become more and more complex, there's more requirement for us to do that because the sequencing of those protocols becomes key. Also, it should enforce some sort of packet validation. It should know the standard. It should know what's expected. It should know what an illegal message looks like or a malformed packet looks like. It should give you the ability to recognize that and just drop it. You know, in the case of an Ethernet frame, when you get a malformed packet, why process it if it's just garbage? At a minimum, it should support the parsing of industrial protocols commands. So read, write is typically what it boils down to in some sort of capacity. It also should have the ability to give you visibility into non-standard OT messages. And I'm going to talk a little bit about that in a few slides from here. But we give you the ability. We support a number of protocols. We tell you right off the bat, Modbus TCP, OPC, Ethernet IP, DMP3, BACnet. Well, what about something else? Well, we give you a way that you can process that. What if the device has some hidden interface so that you can do firmware updates and you want to lock that down? Well, if we are able to parse the packet, just because we don't have a standard interface for it doesn't mean we can't implement some sort of rules on that. It should have a passive implementation. As I said before, it shouldn't have any impact to your existing OT system. No latency or minimal latency on that, which is a challenge because you've got to process a lot of data on the fly. You should also have the ability to timestamp and log events to some sort of central clock. And I know that Chris Sistrunk is a big advocate of network security monitoring, and being able to tie network-specific events to real-world events is a pretty big deal. So having that to a centralized clock is huge. It also needs to allow for a way for the OT engineer to implement his baseline easily. As we said before, there's a skills gap. There's a lot of complexity we're rolling into here. There's got to be a way that you can essentially learn the network, present it in a summary that you can now make informed decisions as to what rules you need to enforce. There also needs to be a way to test it with confidence that it's not going to have an immediate impact with false positives on your system. You need to be able to test it in a non-invasive way. We also believe that the events that you get from this deep packet inspection need to be meaningful. It can't just say instance X, object something, something. It needs to pertain to the real world. What does that mean to the person who's going to see that alarm show up on his screen? And you really need to deploy DPI as part of a whitelisting strategy. So that's not anything I've mentioned so far, but the key part to deep packet inspection in my mind is that you whitelist the known good and you assume everything else is bad. Network security monitors, I mentioned before. I know Systrunk is a big advocate for NSM, and there's even a Twitter handle dedicated to ICS NSM if you haven't seen that. But it's hugely important, the whole network security monitoring there. So anyone recognize the eyeball? Whoops, I went too far. Bro, yeah, good. We got some bros in the house. So referencing bro there. Obviously, it's hugely important. NSM does give you the ability to start doing deep packet inspection as well. It tends to be a centralized point. You need to get that data to it. And that's not trivial. The amount of networks that I've had to troubleshoot, which are all unmanaged switches, that bodes for a pretty complex situation now. If I want to get NSM deployed, I've got to now update all to managed switches and do a span port, or I've got to implement a tap. Either way, I've got to break my network to do that. It's an invasive system to be able to implement that. NSM tends to be passive. And really, all this does is just tell you when bad anomalies or some sort of anomaly has occurred. It doesn't give you the ability to block it or stop it unless you start going to more of an IPS approach. So NSM really is an awareness, which is great. We need it because we don't have it. I think there's definitely a need for that. But understand that the important aspect of NSM is how you respond to that. You've got to have an incident response plan that's swift and knows what to do. And if you were in Mike Asante's session earlier, and he was talking about passive operators, you understand that that's a problem. So I'm not going to spend too much time talking about this, but this is based upon the ICS kill chain from Lockheed Martin. But we know, we've learned this from attacks. We've seen high-profile attacks. It starts with some sort of reconnaissance with open source intelligence. You then weaponize your delivery. You get it into the system, usually with a sophisticated social engineering attack or spearfish of some kind, or in the case of Stuxnet, we know that USB. In the case of Target, with infected laptops, there are a number of examples of that. Then you exploit the host, you install your malware, you maintain outside control, and then you do the bad stuff. This is what you do. And when I say bad stuff, what you tend to do is you try to get a PC that's at level 2. An engineering workstation is the keys to the city. It's dual-homed. It traverses the control network to the corporate network. And once you get to there, you can then escalate your privileges and then do what you need to do. That's the modus operandi that we've typically seen. So bad guy comes in. He gets to level 2. He compromises the engineering workstation. Now he can do some bad stuff. Or we bring in the malware or whatever it is via SneakerNet. Come on a USB drive, an infected laptop. Could even be an implant of some kind. I don't know how much reassurance you have with your supply chain, but how do you know what you're getting is truly untampered and what it's supposed to be? There was a Black Hat presentation in 2015 of a guy that took a wireless module and overlaid it to a Siemens I/O, and even though the Siemens controller was turning the I/O, in the case of an output, turning the output on or off, he had wireless ability to override that. There was no contention. He was upstream of a resistor that allowed him to do that. And you wouldn't know it. You'd look at the box and you'd never know there was anything inside of it. And then the third example we've got here could be a wireless attack vector. Either way, you want to get to level 2. That's where you can do your bad stuff to work your way down to the physical layer. So that's the typical approach. And what we're recommending is a solution called Cyberfence. There is a product outside. We will also have a cabana tomorrow. And it is a deep packet inspection capable appliance that is really designed to sit here between level 1 and level 2. Or again, it could be at level 2, level 3, but really I think this is where the value proposition makes most sense. It's designed for this environment. It can protect one or many devices, and you would deploy this as part of a whitelisting policy. So you understand what normal communications looks like between here, and now you've got your internal perimeter between that. The other thing that's pretty cool about Cyberfence is it has a number of ports on it, one of which can be dedicated to management and or monitoring. So I can now take that port out to my external software, We saw Clarity talking. I know that CyberX is here. You're probably familiar with Indigy. These are all guys that have OT-capable monitoring tools. So we can now span that traffic out to there, or we can use this port for dedicated management. I know that the waterfall guys like to talk about the impact of, or how you can get it circumvent a firewall. Typically, you need access to the management console. So our approach is to just take that management console and separate it and isolate it completely from the control network. And this product, as I said, is designed to go in the control enclosure on the DIN rail. So what do we protect against? We protect you against the port scanning, the abnormal data flows, the potential for human error, a lot of the things that we brought up before. And as we start to get down here, this is where it gets really interesting. The firmware updates, the changes of state to the PLC or the controller or whatever the logic might be, and also attacking unused features and functions. So I won't spend too much time talking about the product. If you do get a chance to come by the booth tomorrow, I'd be happy to talk to you guys. I will point out a couple things here. It does do deep packet inspection. It does have encryption capabilities. The encryption is certified to government standards, namely FIPS 140-2 and common criteria. It does have the out-of-band management port. It does have the span port capabilities. It is also third-party. I think I mentioned third-party validation already as well. So that's a little overview, just to show you how easy we try to make it to set up some of these rules. So in the case of Modbus, unit address, register address, whether you want to check the value, and we go right the way down to the value level specifically for writing registers. DNP3, we try to make it more checkbox oriented, DNP3 being a very complex protocol. BACnet again with checkboxes. This is the generic DPI piece that I mentioned earlier. We don't have support for every industrial protocol yet. We're working on it. In the meantime, if you have a protocol, let's say it's Schweitzer's proprietary protocol of something, we can give you the ability to define your own rules in an XML file by looking at simple offsets and doing some sort of pattern matching. So it's kind of an interim step between us having full support and giving you the ability to control your own destiny a little bit. And this is where you can start to lock down some of the proprietary stuff that we have to reverse engineer, namely like firmware updates or configuration updates. How many of you guys saw this recently, the Modbus Stager? It was a proof of concept that was put out there where somebody is using Modbus devices that are public-facing and taking empty holding registers and using that to store his malware. So he would use them as essentially memory locations. Pretty interesting idea. Ultimately, if somebody has access to your Modbus registers, this is the least of your worries because they can just send an FC90 command and screw it up. But this is a pretty interesting proof of concept, and I took this from a data sheet here. This is a device, we won't say who, but it has a lot of registers available to you that you can do with, and this is what the premise of this Modbus Stager is. And the question I ask you is, do you really need to have that many registers open? Are you using that many? If not, lock them up. Use the whitelisting approach. And ultimately, if you want to protect against critical anomalies, you need to go right the way down to the physical layer. So you need something in between your intelligent network connected device that can handle it. So we've got, I think, some flow control here, some torques, current limiter, speed limiter, protective relay, limit controller. These are all things that should be unintelligent solutions to help protect your ultimate physical process. But it adds some significant cost and complexity. So standard best practices, implement traditional firewall rules, consider the value you get from deep packet inspection specifically for your application, add some sort of logging, monitoring with remote logging would be great, remote monitoring would be great, and then also consider the need for end-to-end encryption to take those insecure by design protocols and maybe add something to it. For those of you that were at the Schneider presentation earlier, you'll see that secure Modbus is around the corner, we hope. Very interesting presentation, but in the interim, you can take that into your own hands and implement your own form of encryption. We will just close out here. So industrial control networks are porous. They're insecure by design. We know that. There are a number of holes, so you have to do something. We have to do something if we want true operational awareness. You need to be able to discern what normal looks like before you can understand what abnormal looks like. So you need to look at mechanisms that will allow you to do that, and I think deep packet inspection is a great way to do that. You also have to look at who you trust. Do you trust your ICS vendors to take care of this? Do you trust that the vendor is taking care of everything and you're good? I would argue the track record doesn't look so good for that. So you need to look at other options. Otherwise, do you trust your risk mitigation strategy on that relationship? The greater visibility you have, the more that you look at, the more control you have over your control system and your ultimate physical processes. And DPI is a great tool to being able to work out where the anomaly is, which one is out of place. Embedded devices, the proliferation of embedded devices mean the challenge for us to protect those relies on something upstream of it, something external. So consider we can't just install a software-based firewall or snort on our embedded device because we will probably break it. And also know that there are a lot of options out there, but sometimes the claims for deep packet inspection are not always true. Some are signature-based, so understand that not all DPI technology is the same. And also understand that while this can be complex to decipher, there are tools and there are ways and there are methods to help make that process easier. So last closing thought here is that, this is a cybersecurity event, but really we're not here to talk about cybersecurity. We're here to talk about uptime and safety. That's the end goal. Cybersecurity is just a facet in having a better handle on what it is that we're doing. So with that, I think we're right on the time. If anyone has any questions, I'll be happy to. That's the first thing that we do. So the first thing we do is just check, does it look right? Is it the right shape, smell, look as the standard defines? And then if it is, then we look to our whitelisting policy. Is it allowed? Is it not allowed? And you could just use it for just checking for malformed packets if you want, and not having any whitelisting if you want. You could even use the device just for monitoring. If someone says, it's too invasive, I don't want you being able to control or break any of my communications, just put it in as a bump in the wire that just gives you monitoring feedback, give you syslog information and alerts, or just using it as a tab. So you can use it in a non-invasive way. Yeah. Any other questions? Yes? I think I'll be retired by the time that changes, so I'll let the next guy worry about it. But no, realistically, you're absolutely right. But I would also argue that even just because you've got encryption, you are still based, unless you've got authentication as well, you have that trust-based relationship. What if this host becomes compromised? It has secure access to my PLC, but if that host is compromised, I still want to do some sort of enforcement. Now, we can't do that on the wire quite as easily, so then it becomes maybe a software enforcement policy of something, but absolutely, yeah, or downstream, yeah, absolutely. I mean, one of the things that we do go to market with is we don't just sell our technology as a box, we sell it as a chip. So the other strategy is that we work with OEMs to take our technology and embed it into their device so that we do help them do the encryption piece.